in the exam. Thank you. We can talk about it now, so we will. And that's first up. Let me get the camera going. And yeah, Sean, can you turn that light to the brown button? Yeah, that one. Yeah, that'll work. Okay. So if I hit record, okay. Okay. Slide. Okay. So last time we talked about something that you probably found useful on question number 1 with the exam. And that is something we used to do some time ago called an x squared t squared plot. It lets you make a value judgment about reflections, whether they are as shown here. This is some Fred Hilterman stuff at University of Houston. This is showing the construct of a common midpoint gather. But this simple relationship that you're talking about here, taking the reflection equation and making a straight line equivalent by putting it in t squared x squared space, you could do that with field files, and that's what you had to do on that field file. Anybody remember, did anybody recognize where that file was from, by the way? You should have recognized it. Did anybody know where it was from? Oh, nobody remembered the Bighorn data? You're thinking, I could have come in here and played with the on the computer, right? Bighorn data. That was Bighorn data. It's where they put down the file and they shoot through it. Common procedure. And the Bighorn, it was nice data, but it had some issues with clinkers. Clinkers are coal beds that catch fire underneath and they burn out. And so you have coal juxtaposed with ash that used to be coal as the fire front would progress, and so that makes for a nasty static. That's the reason you have to do residual statics on that line. But for the most part, the reflections are not too beat up. And so with the, so I picked a field file that was a little ways down that to where it had both front and back data. And then I focused on the one side only. But you could do a quick and dirty look at the front and back and you would see the refraction events. We're about the same, front and back, which tells you right away that since shooting this way versus shooting that way gives you about the same number, you say, there's not much dip there. Nothing that I can't, there's always going to be some issues. And since you're doing a refraction analysis to get the near surface events, if you didn't do it both ways, it's not a big deal. It wouldn't knock you down. And similarly, the t squared x squared is not a common midpoint gather, but a field file. But it's okay. It's okay because instead of getting a more localized velocity that you might put together with other velocities to make a velocity field in 2 dimensions, you don't have that. You just have one file. And if you look at a common shot point gather, this equation is still okay. The only thing is it's now going to be smeared over the it's going to be smeared over the reflector a little bit. So it's a built-in averager. But it's not a big deal. You just want an average anyway for the line as a starting point for velocity studies. And so there's 2 ways to do velocity studies: refraction analysis and reflection analysis. Refraction, we talked about a n layers on a half space inversion for refraction data. And after computing number of n equal 1, n equal 2, we said so you could do that for n equals, you could have 6 layers on a half space. And we used to have calculators that did all that. But to do it like you saw this, it was kind of a tedious thing to do. And then the t squared x squared says, okay, this works fine for as long as you don't go too far out. So there were some reflections. You could quickly say, hey, the velocity is like 10,000 feet a second. Okay? So if that's the case, what's an average velocity? I don't know, 10 or 11 or 12,000 feet a second or something. So you could tell by looking at the t0 divided by 2 and looking at estimating velocity that was about 5,000 or 6,000 feet down. So you probably didn't want to go much further out than 5,000 or 6,000 feet. Because if you did, what will happen is this curve will begin to top over. It doesn't look so good. So that's probably what you wanted to do. So, but you could look at one reflection or two reflections or three. It didn't matter. If you look at more, and we'll get to that in a minute, then good for you, because that's a more impressive response. And here it is. Here is Eichel and Amundsen's book, where they're actually putting in an entire common midpoint gather, or maybe a common shot point gather. He doesn't say, but I'm sure it's a common midpoint gather, which is the more common procedure. And he's fitting a straight line to that, so there wasn't anything keeping you from picking every point, going to Excel, fitting a line to it. But I didn't expect anybody to do it, but you could. And if you got too far out, what you would see is instead of this thing forming a nice straight line, this package out here would begin to taper off because it wouldn't fit anymore, right? It's not cool. So as long as this isn't too far out for how deep you're looking for a reflection, which you can tell by the T0 thing, then those are good things to pay attention to. Just a comment about noise from last time. This is the kind of reflection event that you want to do spiking decon with. And normally what you do is you do statistical spiking decon for an L2 normalization vis-a-vis least squares. There's other normalizations, other decons, all kinds of stuff. But that's what you'd like the data to look like. Not like this here, because if you tried to decon this right here, the procedure would blow up. Your inversion matrix normally has a 10% diagonalization or pre-whitening to it to make it more stable, to make the inversion more stable. If in fact you tried to use it with that kind of data, what you're going to get is Promax is going to give you hate mail and say, I'm sorry, I can't stabilize the inversion. You need to pick more of a stronger pre-whitening. And if your data is that bad, you could say, okay, I'll do a 50% increase in the diagonal, the so-called heavy pre-whitening, and then it would probably still have trouble inverting. But what would happen is eventually it would just recreate what you had. It would be a no-op. Okay? So you need to have the thing work right. You've got to have signal to noise that is as good as possible, because remember what it says. It says the noise is 0 for spiking decon, and it's never 0. So, you know, you don't necessarily have data looking like that, but that's what you'd rather have, data looking like that than data looking like that for spiking decon. So you do it post-stack. Yes, Sean?
Whitening.
Whitening. What they mean is the inversion matrix, if you diagonalize, that is to say strengthen the diagonal in the inversion matrix, it becomes like a Dirac delta function. It just recreates what you already had. Okay, so if you diagonalize the matrix to where it's 90% whitened, it's just an inversion matrix doing nothing. It's a Dirac delta function, or approximating it. Okay, 10% is to let it do the inverse operations and be stable in the process. So it gives the inversion procedure a stability. And so that's common. If you look at the default parameters, it'll say 10% pre-whitening, and what they mean by that is in deference to the Fourier equivalent of that, where you're increasing the bandwidth, right? And increasing the bandwidth, meaning whitening the bandwidth. That's just the term they use. Speaking about the electromagnetic oscillation, which if you have all frequencies, you got white light. Okay. Yeah. Good question. It's jargon. And if you take Bob Sheriff's book and you look up pre-whitening, you're going to get a real good explanation of it. So yeah, it's the sort of jargon that 40 or plus years of experience, you say it and you realize you just lost your audience. So thank you for telling me you lost me. Okay. All right, so that's what you do with that. You know, and the other thing is, so here's this constant velocity stack. If you kind of look at this and say, okay, that one's pretty good, that's real good, I've gone backwards, and you say, okay, that's the right velocity. This is landmark. You probably say, okay, if that's the right velocity, then anything down here is not a primary. Okay, you can't go backwards. Not in a situation like that. Not a marine survey. You're not going to go backwards. However, it makes this weak reflection right here look pretty interesting. Okay? A little bit further down and a little bit faster. That looks good. Okay? So I really like constant velocity stacks because they give you a pretty good idea once you get used to using them. And what I commonly do is if I've got a short line and I want to see that whole line, I'll take every fifth CDP. You just go into and say, okay, give me all the CDPs, and then say, give me every fifth in parenthesis on the input style for this data input, and give me every fifth CDP, and then I will actually do 10 or 20 velocity panels with every CDP of the line. And so you just keep getting the same line over and over again for these constant velocities. Now, I never do that for marine very long, because then the velocity spectrum is so much better. And so you make your guide bars with your velocity, constant velocity stacks, and then do your spectra to really trim it up. I never move from this when I'm doing land data. I never look at spectra. They're a waste of time. They're just so busy, you can't tell what's going on. Now, I've got an example today when we're talking about the dip move-out correction, and I have never seen data that good. So if somebody says that's real data in the mountain front, I'm saying really. But, you know, for the most part, in land data, I never move to the spectra, and in marine data, I rarely use this very long just to get me started, and then yeah. Okay. And then the velocity, the interval velocity, and again, depending on what you did with your homework, there was more than one reflection. And so you've got several points here. First off, if you start building your little table down here, you say, okay, what do I have? And this is velocity increasing this way, and this is two-way time, or T0 time, if you will, increasing this way. Now, on your t squared x squared plot, at x equals 0, t equals 0, you've got a point. That point is x equal to time is 0, and the velocity is something. And a good first approximation for that velocity would be the velocity you got for the direct wave. Piece of cake. So your first point on a good velocity spectra for a t squared x squared analysis of this package would be 0 time and the direct wave from your refraction analysis. You don't have to do that, but that's not a bad way to start. So that gives you a point right there to start off with. And then you've got a reflection here, and if you don't go out too far, say about to here, then you could make picks, maybe you could make picks here and here and here, fit a straight line through it, get a T0, and get a slope, and now you've got a second point, say here, on your spectra, on your analysis, building velocity function, I should say. And then the third time you do this, you have another reflection, and you maybe pick, say, 3 values, and draw a straight line. It intersects at a T0. It's got a different velocity, say maybe here. And then that last reflection, if you were so bold to pick deeper into the data on the Wyoming data, then you'd maybe pick 3 points again. 3 is good because that way you can define the line better. and then that'll give you a t0 and a new velocity, say here. Now once you've done that, then interval velocities are possible. This is the Dix equation. So here is the Dix equation. And so I can get the interval velocity from this time and this time. It would be that difference, time difference. And then the second VRMS is the one labeled sub I by Hilterman here. And the first one is this one here. So that's simply plug in the numbers you get here and get interval velocity for this first zone, zone number 1. And you can do that again for a zone number 2 and a zone number 3. So 3 intervals for 4 points, okay, no problem. Once you've done that, you can, if you want to proceed, and get thicknesses for all of those zones, 1, 2, and 3. And then similarly, you can get an average velocity by summing up those 3 zones and dividing by the biggest time, which is this time down here, or I should say this time down here for that 4th point. When you do that, you'll get an average velocity that's different from the root mean square velocity, because that guy is an average but not your standard average that you've seen statistically since you were in 6th or 7th grade. Okay, that's just a hands-on way of analyzing data without having a computer do it. It's called, just for lack of a better word, Fred calls it an expanding spread. That's because he's got a particular acquisition technique he normally uses to do that back when, but it's just t squared x squared analysis. And then, not to kick a horse, this is just a picture we talked about last time of what a multiple looks like on a velocity spectra, and avoid it. But today we're going to talk about the dip move out relationship, and so you'll see that I have to kind of temper my discussion on this.
What is the VB and VT?
Let me go back to this slide here. Who knows? Velocity multiple, velocity primary, velocity don't know. That's what I would. I don't know what that is.
Oh, actually, it's velocity
between multiple and primary used in generating. I don't know. Yeah, it wasn't the point I was using the figure for. Somebody knows that, whoever did that paper, but I don't know the answer. Okay, so that was last week, and that. So again, to do the problem number 2 from VSP was kind of a recapitulation of Bob Corbin's discussions dealing with what are the values of VSPs, and problem number 1 was one of those deals where you had to go back and revert to primary tools that have been incorporated into programs that you get used to using without thinking about the labor they are solving for you, if you will. All right. Now today, what we're going to be doing is we're going to be talking about migration. This will kind of complete the circuit on the details of processing. A couple things I want to mention. First off, always, some of you haven't just joined the SEG. You're welcome to do it. It's free. I'll just pass around. I receive 5 of these every month. The leading edge shows up, and I put them in the library, and I pass them around, put them in people's boxes. But you're welcome to take, if there's 2 copies in the library, take one home. It's okay. So I want to mention, I handed this out to some people the first day, but this is a kind of a silly paper, but it's about an interesting subject, and that would be Clarence Karcher, who invented the seismic method. And one of the things I'll mention, and I'll pass this around in a minute, is that the very first seismic data he ever took in the 20s, he migrated the data. And that's the discussion we're going to be talking about today, migration. So there are three things you do in processing for sure. One of them is filtering, frequency filtering, maybe spatial frequency filtering in the FK sense. We talk about deconvolution, okay, all that's filtering in one kind of collective statement. The second thing was taking advantage of the power of the common midpoint gather and the stacking process, picking the right velocity, and improving the signal-to-noise ratio remarkably. And that's revolutionized the business, continues to do it. If you're, Sean's in the other class, and Peter I came in and talked about having stacks of thousands of traces, taking advantage of the square root of n. You know, I used to think a significant fold of stack was 20 or 30. Today, they're shooting so many traces, and they find that the high fold, especially when you have point sources and point receivers, no arrays of receivers or sources, that they get an improvement consistent with that square root of n, even into the thousands of traces. So it's money well spent if you get a return on your investment like that. But if you look at the ProMax overview on the subject of migration, then one of the comments they have is, it says, according to Bob Sheriff, and again, he's the author of that book that I've shown you several times, migration is an inversion operation involving rearrangement of seismic information elements so that reflections and diffractions are plotted at their true locations. That's kind of redundant, I think, because a reflection is nothing more than a series of these coexisting diffractions making up the boundaries of geologic boundaries. But further on this discussion, and again, this is still looking at ProMax, the help command, migrations come in a wide variety of categories. And the first one I want to talk about is it's talking about two different kinds of migration algorithms. But a migration algorithm, inserting migration, which uses root mean square velocities analytically and does not account for ray bending at interfaces, is characterized as a time migration. That's irrespective of whether your final section is shown in time or depth. Time migration says straight rays, root mean square velocities, no attention to Snell's law. And of course, not mentioned in here is it pre-stack, post-stack, okay? So what do? Well, we do in here, in the lab, we do post-stack, time migration, Kirchhoff algorithm, time domain. I mean, that's commonly what we normally do. Now I think I don't know whether Gulce showed you the Stolt migration. That's an FK migration, but that's a real quick algorithm. It's got its own peculiarities, but in terms of migrations in the time domain, what I just said is true. On the other hand, a migration algorithm which uses interval velocities and accounts for ray bending with the Snell's law is characterized as a depth migration, and that again is whether or not it is displayed in the time domain or depth domain. Many of you found out in the last class, sometimes when you go to show your section as a depth section, it looks like it looks odd. It looks really strange compared to the way your section looked like in the time domain, to the extent that you wouldn't show it to your best friend. It looks distorted, strange. And so you'll see mainly most seismic products, when you're talking about the kind of work we're doing in this 2D lab introducing the topic, we stay in the time domain. Because to go to the depth domain gets into an area where you're a little bit over precise. How would you say? You don't have the precision necessary to do that. And so all of the warts of your velocity function get magnified and kind of distort your image, looking like a fun house. And that's just the way it is. You have to, but I used to say that reflection seismic, was an imaging process, and these days it's pretty much a model-based process, because virtually everything today that comes out of a shell oil environment for people to work with, is a model-based procedure for pre-stack depth migration. So it is accounting for array bending. Whether it's shown in time and depth is irrelevant, but they build a model. And in a sense, and I'll show you some at the end of the discussion today, the model they build is the answer. The section they compose from that model just confirms the answer. So all of this, you know, they look at a section, they revise the model, look at a section, revise the model, and they iterate down to where they're really happy with the model, and they run a section and they say, yep, that's the best we can do. Really, the model is the answer. The Earth looks like this from a velocity standpoint, according to these data. So it's a model-based procedure entirely. There's other terms about migration, whether or not it's in the distance domain, the time domain, whether it's in the frequency domain, FX domain, FK domain, and there's a lot of different things about that. Let's go back to some definitive pictures, and let's try to understand the two things that migration does. And the two things that migration does is it shows the structures you're trying to image in their proper place. It puts things in the right place. And it furthermore collapses diffractions, which really are composing these items, into a point source. Okay? Now, again, I'll just pass this around. I need it back because it's the only copy I've got that's actually of this. But this is Karcher working in the 20s, I guess it was, 21, doing reflection seismic. And what you're going to see in a minute on that page I have open to, we open to the staple, in the lower right-hand part is what we're going to talk about next. This is how we used to do migration, and it lets you to understand what's happening in the process. So this is the interface that you're trying to image. This is the boundary between two geological materials for which a reflection is possible. Okay? Now, these CDP points, these common midpoints, number 1, number 2, 3, 4, 5, 6, are common midpoint gathers that you have collapsed to a single T0 trace. Now, for this illustration, I'm going to do the same thing Ozyl-Maz does. I'm going to say that the velocity is 1. And therefore, time and distance blur. When I can talk about depth, I can talk about time. It's the same thing. If I say velocity is 1, which is fair game. So here's the issue. If we have a common midpoint 1, and we get a reflection that occurs from this location, we've already done a partial migration. We had a source here and a receiver here. We took a common midpoint in the middle. And in the process of picking that spot for the display of our data, we have done a 0th order migration. It's basically a 0th order migration. Okay? And we take the results we get coming from this F point captured by this common midpoint number 1, and we post it right there underneath that common midpoint gather. And then we do that for number 2. The reflection event came from here, and we in fact post it directly beneath the common midpoint gather at that location here. So E becomes E prime, F becomes F prime. Similarly, number 3, D, that point becomes D prime, directly beneath the common midpoint gather 3, and then ad nauseum C, C prime, B, B prime, A prime. Now we have defined an apparent reflecting surface in time. If you then have 6 common midpoint gathers, or 60 is better, now you're going to be able to define, by the connection of all these points, a surface. And that's going to be the surface shown in red here. So that's going to be the apparent reflecting surface in time. When in fact the true reflecting surface is this item shown that I've marked up. And again, the velocity is equal to 1, and therefore this could be distance, depth, or time. It doesn't matter. Now the question is, what you'll see right away is if you look at the true dip angle, theta, between the actual boundary and horizontal, that angle is going to be smaller, it's going to be bigger than the apparent angle that you would have if you measure this apparent angle for this reflecting surface in this figure. So what Karcher did, wherever that is, what Karcher did in the lower right hand is that he said, and he came from the physics community, so he knew what he was talking about. He said, you know, I don't know where this reflection came from. So somewhere on this arc, this reflection came. I don't know where it is. He didn't know anything about it. He didn't have sources and receivers, and he didn't call it a common source point gather, and he didn't know anything about a common midpoint. It didn't mean anything to him. He said somewhere on this curvature, we got, this came from there. And so following that lead, what you do is you take a simple protractor and you put it on the common midpoint and you extend it to F and you swing an arc. Now I'm going to swing it out here as well. Here's the arc that is swinging F prime, and it comes in like this and continues to there. And now I'm going to swing an arc similarly from common midpoint number 2, and I'm going to start it at E prime, and I'm going to swing an arc and continue that. That's just what Karcher did. And what he found was that surface that is defined by the coexistence of all of these arcs is the true surface. So if I continue to do this, I begin to define this actual dipping surface much better. And if I did that ad nauseum, not with 6 points, but with 60, I would have just drawn in that surface. Okay? That's how you used to migrate seismic data. You would take the results you got, and you took basically a little swinging device, and you would migrate the events back to a place that became the locus of all point that was defined by this swinging of arcs. Now this is pre-computer, but it does kind of set the stage for what is happening here. Now mind you, if that's flat or nearly flat, it's trivial. You know, it doesn't move a whole lot to work. And so when you swing the arcs, it's just like they run together. But when you have some significant dips, then you end up with this situation here. And this is discussed. I can tell that it's in geophysics, because I know Jasowitz and the leading edge didn't start being published until 1982. So this is in geophysics. This is from Oz Yilmaz's book. And anyway, Jasowitz and Chun showed the same exact thing here. And what they said is that this section that they show here, when migrated, is moved up dip, their discussion right here. It's moved up dip, steepened, and shortened, and mapped into its true location. So similarly, what I'm showing here, when I do this swinging of the arcs and find the new surface, that new surface is up dip, it's shorter, and it's steeper than the other one. So that the angle I get is going to be the true angle theta with norm against the horizontal. Okay? Not the apparent one that I had before I did the migration. Now this is all pre-computer. Well, what's the second thing a migration is supposed to do? It's supposed to move things to the right place, and in doing so, again, up dip, shortened, and steeper. The second thing it's supposed to do is to take a diffraction and collapse it to a point. Now, we talked about this before. If you have a single point in space and you have a series of recording geophones on this surface here, then this one's going to receive it first, These two here are going to receive it second, and so forth, so as to create this, this curvature right here that is in fact a diffraction hyperbola, because that little infinitesimal point acts according to Huygens principle and creates its own signal and gets recorded, and that's what you get. Okay? Now, what we did before was we swung arcs to find out the new location of the correct interface. And when you do that, you'll find, hey, it's not back here. These arcs don't converge back here. It's up here. And they begin to converge, and end of story. Well, what about this? If you take that same protractor and you tie one end to this point here, and you swing an arc going through this point here, and you do that for all those points, this is what you get. What it does is it takes all of the energy that the Huygens principle has spread out into a diffraction hyperbola, and there's only one spot that's in common with these arcs. And that's to say, you could in fact do that with data pre-computer, and that's how you would tell, well, that was just a diffraction hyperbola, it collapses to there, and Now, of course, if you have a whole series of these, that defines a surface, and here you go, right? All right. Now, let's talk about post-computer, and the best way to do it for the algorithm that we use here, which is the Kirchhoff post-stack time migration, okay, is to use something out of Claerbout in 1985. He's the professor emeritus at Stanford, had the Stanford Exploration Project for a number of years. And I'm sure he's writing in geophysics here, perhaps the leading edge, most likely geophysics. But this is kind of a classic example. And he shows a harbor that has a breakwater. You know what I mean by a breakwater? That's one of those little notches where it protects the moored boats in here from storm waves coming in. Okay? So if you have an incident wave from the ocean that's maybe come several thousand miles, and so now it's a plane wave, and it hits a notch like that, what you're going to get is a series of semicircles that are going to move out looking like Huygens principle, past that storm barrier and hit the harbor. Probably much diminished, but that's what you're going to get. Well, here's a picture of it in XZ space. So this is X and this is Z. And in XZ space, recordings along the beach here or along the harbor is going to be associated with these semicircles that are then coming in to in the receiver cable and like this. But if you record the times received by the receiver cables and move from XZ space to XT space, then that's when the semicircles become then diffraction hyperbole. So in XZ space, the semicircle is the appropriate mindset. In XT space, it's a diffraction hyperbola with all of the elements of that conic that we've had. So, if you have then a single spot in your XZ space, and you take a picture of it like we talked about before, no surprise, you get in the time domain, unmigrated, this diffraction hyperbola. Furthermore, if you have two together or four or five together, they begin to define a boundary, and if you put a whole bunch of them together, they in fact define the boundary with diffraction hyperbolas coming off of either end. This is the first computer algorithm used to do migration in the time domain. It is a procedure, a series of procedures known as diffraction summation. And Kirchhoff is simply diffraction summation with attention to the waveform and the specifics of that. In fact, the specifics of all of this is described in Oz Yilmaz, Volume 1, and beginning on page 484. And so what you have is, this is unmigrated, and this is migrated using the Kirchhoff algorithm. And the Kirchhoff algorithm uses this equation to sum up time events that start with an analysis at point A in the unmigrated region and say, hey, give me all points defined by this time equation for a particular tau and a particular root mean square velocity, and plot them in this migrated domain. Now, if you've got the right velocity and you're testing that algorithm for that exact point, then you will find that diffraction hyperbola. You'll sum all those values up and you'll get a pretty big number. If you try that same game here, then you'll sum things up. You'll have the right velocity but the wrong point, and you'll get like, you know, maybe a very small number, maybe 3 orders of magnitude less. Okay? And so for any choice of root mean square velocity, and for any other points but this one here, for this very simple figure, you won't get near the collection of points that are summed together to be replaced and deposited at this point A. So you send out a tracer with that equation and say all of those times for those offsets, I'm going to add them up and I'm going to deposit them where at this point A in the new migrated domain. When you do that, you're going to get a big value, and if you normalize the resulting migrated section, you'll get one spot and everything else will be effectively 0. Okay? That's how the Kirchhoff migration works in the time domain, post-ACT. It looks for diffraction hyperbole that have been building blocks in the forming of all of those images that you're seeing, and it says where do they need to be. And it does it in a building block issue. It says where do all these little diffractions, kind of like a Fourier decomposition, that have created these images, where do they need to be? And it sweeps them out, and all you've got to have is the right root mean square velocity, and then just plug it in into your unmigrated data, and out will come, in this case, just one spot. That's Kirchhoff 2D post-ACT time migration. The only difference is, instead of a simple diffraction summation, it does pay attention to some of the distortion issues particular to the wavelength, and it's described again in Ozzie-Ilmaz. Now here's the other thing. What if in the unmigrated section you had a spot, a piece of noise, not real, right? What's that going to do? If you run the Kirchhoff migration algorithm on that, what you're going to get is this smile. Okay? So if you're doing migration, Kirchhoff 2D post-ACT time in here, and you have data that are kind of spooky, like poor signal to noise, and you run the migration algorithm, you're going to get information down to some point, and from then on, you're going to just get a lot of scallops looking like this. And this is basically the impulse response of the Kirchhoff algorithm to a spot on the unmigrated section. So the impulse response will be the only thing there, nothing real, and so you'll get a series of smiles when you have no signals. So it'll actually look like there's something organized down there, but trust me, when you start getting nothing but a bunch of smiles, you've gone into Never Never Land. You got no data. If you have a series of frowns, you might still have diffraction hyperbole that are showing up because you had the wrong root mean square velocity and you didn't collapse them right. Okay? So frowns are kind of good in that you still got signal, you got the wrong velocity on the migration. Smiles tell you you're way down below your real signal. All you're doing is looking at the impulse response of the Kirchhoff algorithm stamped on top of yourself. And so you'll see that when you have good data and bad data. On the landmark, you've got nice reflection events, and then you've got this kind of diapiric looking thing on the right, and kind of inside of there is like, I don't see any differentiation in there, like it's a salt plug or a shale plug or something. You don't know what it is. If you do the migration, you'll get a lot of smiles in there. There's no signal in there to look at. Okay? And that's simply the impulse response being printed on the migrated section. It's a really good way to find out where your signal to noise is below the point that you can recover it with procedures like filtering or decon or any of those things. Okay, so let's look at a few figures to look at unmigrated and migrated figures, just to get your mind around this. Again, this is the work of Fred Hilterman when he was a grad student. He did his dissertation on actually building in a water tank little images, and he used a spark plug and a bunch of receivers to actually make seismic images of certain features to look at migrated events and as to what they were supposed to be looking like. So here is one of his figures in a water tank. It's simply nothing more than a simple anticline flexure that has, of course, an axis going this way, and he's recording along a traverse over this anticline that makes the following imprint, on that feature like this here. And so the migrated true image should be this feature right here. This is what it should look like. But what you get is shown by the data. Okay? So the features in the subsurface are muchly distorted prior to migration. If you don't do migration, you'll have a very rude awakening on your understanding of what's down there and what it really looks like. Now I go to this at this point because I always put, I marked out the word either and I put a period right here and I said is a minimum. Okay? Now I want to say that let's look at Fermat's least time principle, this time without putting the period, and look at all three possibilities. Now mind you, Fermat is building reading glasses. And so he's looking at convex and concave lenses and their effects. Okay? And here's why I'm talking about this now. Because here's Fermat's least time principle, which assumes that the travel time could be a minimum, it could be a maximum, or it could be a stationary point, an inflection point. Okay? Because for pick an offset, say right here, which would map, say right here on this model, this is not an anticline now, this is a syncline, like that. It should look like that. He doesn't show it here, what it should look like is not that, right? And what you get is this strange looking bow tie. Now, not to be confused with gow tie. No, just bow tie, not gow tie. Gow tie is nice looking. This is strange looking. Okay. All right, so at this point right here, what you get is this value, and this value. One's a minimum, one's a maximum, one's an inflection point, as per Fermat's least time principle. All three areas accepted. Okay, so there's only one time, and he's worried about glasses, so he sees this kind of thing a lot. But for the most part, Fermat's least time principle, we can say is a travel time minimum. But in fact, sometimes it is a minimum, maximum, and an inflection point as per a syncline that has what's known as a buried focus. And by that I mean there's some structure in the ground below the plane of observation, vis-a-vis this is where you're working with your seismic, such that when you look at rays coming off of this, the focus of that particular convex downward structure is beneath your observation place. So you're trying to see the seismic data up here. The focus is here beneath you. Here's the feature. And what that's going to cause is one of these bow ties. Okay? With a forward leg like this, a reverse leg like this, and then this strange connector that comes in like this to complete this feature. And again, when you migrate that, it'll migrate back to it's a standard feature. And of course, here's an exercise to try it yourself. Here's some examples on here is a feature that will migrate into, let's see, before and after is, yeah. This feature here will then, the correct feature is shown here. And these are some examples here on this. And just some other features. Vertical fault will look like this. You'll actually have a, it'll go somewhat beyond here, and it won't look like you would imagine it. I mean, you can do these kind of features and say, wow, that distorts my thinking as to what was there. That's why migration is not an option, it's quintessential. You have to do it. If you don't do it, and you go to do the interpretation step, then you can be in a world of hurt. Now, let's look at the way some of these features would look. So here is an Earth model that has the following kind of humps and bumps. And what would that look like? And then below there is this layer. And below there deeper is this layer here. 1,500 meters a second, 2,000, 2,500, 3,000. Model is not particularly crazy. The first feature, this top layer only, is going to look like this. And so here's time, kind of hard to see with my blurry figure. And you're going to get this kind of a feature from this structure here because these events here have a convexity such that they have a buried foci, and so you've got two bow ties kind of confusing this whole issue as to where you would say, I don't know what we've got. Now you'd say, well, I can see something's crazy here. Embed that in one-to-one noise. You don't know what you got. You just say, what is this? Okay? And migration algorithms will work in the midst of noise better than certainly decon, but still you'd have a hard time understanding what you've got. The second layer, those rays that go down through this and try to image on this second layer would look like this. So now here's the second layer, and you see it has some artifacts caused by the humps and bumps, as it were, of the first layer. So you'll have these scars from the rays trying to image the way things really are. And then thirdly, images from this third layer look like that. Put them all three together, this is the image you get pre-migration. And somebody wants to position a well. You got nothing. And that's not uncommon. That's what you're looking at, unless you try to unravel that with the right migration algorithm. Okay, I said the word right migration algorithm. Let me go to the thing that really got this off dead center. Institut François Dupetrol, IFP, EFP in Paris. It's in a suburb of Paris known as Malmaison. And I've been there, and they started a really interesting thing. The pre-stack depth migration was just getting started. And so they put together an interesting idea. They built a model like this. That's a velocity model. And each of those colors represented some exotic velocities in this exotic structure. And they knew the answer. They did very careful imaging of this structure and had field files that had this structure, and they said, find out what the model looks like. Wouldn't tell anybody. And put this in front of the industry as a challenge. And you'll see this today. This was in the mid-80s. And people were just starting to do pre-stack depth migration and had computer power to do it. So the Marmousi model is still alive, and you see it occasionally bouncing around the literature today. And so in the 80s, my colleagues at Conoco, developing pre-stack depth migration, used to stay till 5, 6, 7, 8 o'clock at night working on the model to try to have Conoco be the standard bearer on migration algorithms. So that's the sort of thing that that kind of got it going. That was about the time frame when migration began to really take off. This is an example of what happens when you have this kind of a structure, and when you do a migration algorithm, you end up with this wedge, and you say, well, what's the deal? I can't even see anything in here. And the answer is, you're migrating this stuff here. It's got to go up, dip, shorten, and all that, and you pull in values that you didn't have any data for. This is fake data. This is your computer program looks beyond the actual data and brings in noise and tries to connect it. Okay. That's why if you're trying to image, say, a zone this big, and it's quite a ways down, and you've got some clever acquisition and processing techniques, you have to take the data like this. So you take data maybe from here to here to image this, because otherwise the information here is off of your, so if you have a steep structure, you have to see it here to put it where it really belongs here. Okay, that's why the apron, if you will, around a survey can be so big. Okay, so that's you'll see that commonly, and there's a good example of what happens if you don't have sufficient coverage beyond the zone of interest when you do a migration in steep dipping rocks.
Will that wedge get rooted in the data somehow?
Oh, go back to Howard and I doing the random noise data, and when you actually imaged it, if you aggressively process it, you might create, seeming sensibility out of what was nothing. Yeah.
I mean, in that particular example, it looked kind of weird.
Well, it depends on how your computer program is working. In other words, if somehow those were null values like -999 or something, the program should today say, well, that's not data, and it should leave it blank. I think. But at least then, it would reach beyond the dimensions of your array and get something and bring it in as data. Because
I think this is the same event that we saw in the previous slide, because our velocities are not occurred, so we were having some blank.
Right. Well, exactly. And in the case of Promax today, it pulled up something looking like blank. In the past, it depending on how it worked, it could bring up something in the computer that happened to occupy those spaces, in a sense, from your dimension statement that might be, like not null values. And yeah, you saw in the lab, yes, because when Gulce was doing the depth migration on the landmark structure, she had some data at the bottom that was blank. Yeah, she had pulled that from, it's a good example of it. And so the prudent way to show that is you cut it off. You stop your discussion at, say, 3.5 seconds, so as not to show all this, because it's wacko. I mean, there's no data there. So it does, but yeah, time was it didn't do that. But it's better now to see that, because everybody knows what is that. It's not data. Yeah. Right. Okay. Let's talk about dip move out. You may or may not do this in lab. I don't know what Gulce has. We used to do this in lab, but it's become a little passé. I still mention it because it's a real problem that's handled today with pre-stack depth migration. And you can read in your own slides at your leisure what he's talking about here. He being Dave Hale. Dave Hale did his dissertation at Colorado Mines, and which became the dip move out algorithm. At the time, I'm processing in the 80s a lot of seismic data that looked like this. I was in the, say, Calgary area, and I would have most of my lines in the Calgary area looked like that. They were flat areas, and then I would run into the thrust plane around Banff, and you had very bent rocks. And so if you're working on the edge between that, you're having a tough time imaging something that's very flat juxtaposed with something that has substantial dip. Okay. And here's what happens. So here is a common midpoint gather. that is previous to dip move out being run, and you would have this velocity spectra. Now what I've said before is you're safe to pick up in here, come on down here, but avoid this because that's meaningless. And I wanted to make a little statement about it. You know, all generalizations are false, including the one I just made, right? Here's a good example of where you have to kind of change the rules as to how you pick a spectra. Anytime you're dealing with something as abstract as a velocity spectra, you know, you do get some, you know, it's an abstraction. What is going on here? Well, what's going on here is that you have one velocity function you can pick here that's associated with the steeply dipping events. And there are some events like this and like this that will flatten when you pick those velocities. Other events, like these guys here, are still improperly moved out because they're associated with flat events. Okay? Similarly, if you pick inside of here, you will flatten events like this, whereas you have turned now inside out events that were from the steep dipping thing. So again, steep dip function, flat dip function, played out on one common midpoint gather, what to do. Okay? Dave Hale came to the rescue, and it's a tedious process using common offset gathers. And it's written up in Promax. You can read it at your leisure. But you gather your data into common offset gathers and migrate. Basically, it's a partial migration called dip move out. And so what happens is your initial velocity function, which looks like this, having both steep dip and flat lying functions, gets turned into a velocity function like this, that when you pick it, it corrects all things equally. So for a while, people, even operating in areas that had no appreciable dip, found a real data improvement to do this partial migration known as dip move out, because what they found was even if they didn't have steep dip issues, that the partial migration offered by dip move out really improved the whole velocity analysis process. These days, again, it's pre-stack depth migration, so dip move out again is kind of passé, but it was an important bridge. When I was processing data in this kind of a region, I used to make two sections. I used to make one section with the flat events, and I make a section with the steep dipping events, because I was faced with the same conundrum with the two different picks on the